Look closely at the empty space in your living room right now, and you'd see a dense, crowded storm of radio frequency waves. Every second, invisible electromagnetic energy is colliding and bouncing off your walls. This microwave oven is a heavy emitter in that space. It operates on the 2.4 gigahertz frequency band, an unlicensed slice of the spectrum that government regulators left free for anyone to use. Your Wi-Fi router, your baby monitors, and cordless phones are all competing per Ingratine on this exact same frequency. Transmitting delicate digital data through this environment is difficult. To prevent a signal from being drowned out by the background noise of other appliances, a device needs a specific strategy to ensure its data survives the trip. Short-range wireless communication is a constant cycle of navigation and recovery. To maintain a link, a device must actively fight for its place in the airspace against a backdrop of constant electronic interference. The origins of the technology are represented by these carved Norse runes. They belong to King Harald Gormson, a 10th century Danish king who consolidated separate tribes into a single kingdom. The technology shares his initials, Ha and Ba, because its core function is to pull separate pieces of hardware into a unified pair. To find a partner in the chaos, a device initiates an inquiry request. It broadcasts a signal into the room, asking any available technology nearby to identify itself, its device class, and its available services. Once two devices agree to connect, they execute a pairing process to establish a trusted bond. They generate and exchange specific cryptographic keys, securing the connection with AES-128 encryption to prevent unauthorized access. This handshake generates a shared link key used for authentication. By referencing this unique identifier, the devices can verify the source of every incoming packet and ignore any signal that doesn't carry the correct cryptographic signature. To avoid interference, the protocol divides the 2.4 GHz band into a grid of 79 distinct channels, each 1 MHz wide. Instead of staying on one frequency where it could be blocked, the devices use frequency-hopping spread spectrum. They continuously jump between these 79 channels following a pseudo-random sequence known only to the paired pair. These jumps happen every 625 microseconds. This results in exactly 1,600 individual channel hops every single second. If another device is jamming a specific channel, the data point only occupies that space for a fraction of a millisecond. It instantly moves to a clear frequency, ensuring the stream of information remains uninterrupted. By never staying in one place, the connection maintains its integrity. The devices simply hop around obstacles, finding clear paths through the crowded air. To keep those 1,600 hops per second perfectly synchronized, the connection uses a master-slave architecture. The master device dictates the timing and the exact hopping sequence, while the slave synchronizes its internal clock to follow. Communication is organized into rigid time slots through time division duplexing. The master transmits data in even-numbered slots, and the slave responds in the odd-numbered slots, allowing information to flow in both directions without collisions. Each slot carries a data packet. Right after the access code used for synchronization, the packet contains a payload of digital information, often consisting of compressed audio data. When these packets reach your headphones, an internal codec decompresses the payload. This data is then fed into a digital-to-analog converter, which translates the numerical code into the electrical signals that drive the speakers and create the sound waves you hear. The audio we hear is the result of a meticulously timed exchange, where billions of digital packets are sorted, synchronized, and converted into sound in real time. While audio streaming requires a continuous stream of data, other devices have different needs. This glucose monitor is severely constrained by its small battery, so it uses an approach called Bluetooth Low Energy. Unlike a pair of headphones, a low-energy device spends the vast majority of its time in a deep sleep mode. It remains disconnected and inactive to preserve its power supply. The device briefly wakes up for a few milliseconds to broadcast advertising packets containing sensor data. Once sent, it immediately powers down again. This shift from continuous streaming to intermittent bursts is what allows the Internet of Things to function. It enables sensors and smart devices to operate for months or years on a single charge. This architecture allows for complex networks. A single smartphone can act as a master node, coordinating a Piconet that manages simultaneous connections to a smartwatch, a fitness tracker, and a car audio system. Newer versions of the protocol have expanded these capabilities further, introducing mesh networking. This allows devices to pass information to one another, extending the effective range across entire buildings and industrial facilities. The 10th century king Harold Bluetooth unified separate regions under one crown. Today, his namesake protocol provides the technical framework that allows billions of independent devices to interact. By combining high-speed frequency hopping with power-efficient transmission modes, Bluetooth allows a diverse ecosystem of peripherals and sensors to communicate reliably within the same crowded airspace.